So far in our discussion on partial order relations, we have come across these terms like maximal elements, minimal elements, greatest element, lowest element, upper bound, lower bound, least upper bound, greatest lower bound. Okay, and these things are because of the fact that if a relation is partial order relation, there is an order in some of the elements of your set. When the function is reflexive, antisymmetric, and transitive, if only these conditions are satisfied, then what is guaranteed is the elements that are involved in the ordered pairs. Okay, among those elements there will be an order, and if the elements that are involved in ordered pair happens to be all of the elements of the set, then it means what? It means there's an order in every element. What I mean is very simple. What I mean is that, let's say if one is going to be related to 2, then clearly 2 is not going to be related to 1. Okay, and we represent this fact as 1, 2. This is how we represent a partial order relation. Okay, and of course 1 is related to 1 and 2 is related to 2 because of reflexivity. Okay, and because we add a condition of transitivity also here, so what happens is that if 1 is related to 2, clearly it means that 2 is not related to 1, so it is going like this, 1 to 2 in this direction. Okay, and if to add to it, if I say that 1 is related to 3, sorry, 2 is related to 3, if we add to it, if I say 2 is related to 3, now from 2 it will go this way to 3. Okay, and clearly it means that 3 is not related to 2. What it also means is that 3 cannot be related to 1 anyways, anyhow. 3 cannot be related to 1. This is the order that it will follow. So because of antisymmetric, this cannot be happen, this cannot happen, and because of transitivity, this cannot happen. Because if 2 is related to 3, and if 3 is also related to 1, then 2 becomes 1, then it will not remain antisymmetric. So because of these conditions, antisymmetric and transitive, the elements that are involved in your ordered pairs. So what are the elements that are involved in ordered pairs? 1, 2, and 3. How? Because your relation is now 1, 1, apart from, these are the reflexive pairs. So apart from this, in your reflexive pairs, 4 and 4 will also be here. But now, if 1 and 2 will be in your partial order set, these are the elements, 2 and 3. Okay, 1 and 3 because of transitivation. That's it. Okay, so with 1 and 3 will also be your ordered pair because of transitivity. So this is what you are getting. You are getting an order among the elements that are involved in the ordered pairs. Okay. Now, because of this order, of course, this is not the Halsey diagram. The conventional way to draw a partial order relation is not in a horizontal manner, and also you don't show the transitive edges. I'm not showing the reflexive edges. So you know that what a Halsey diagram is. In the Halsey diagram, I will represent it like this: 1, 2, and 3. Right. So of course there's an order, and right now there's an order between 1, 2, and 3. 4 is not involved in that order, so this is a partial order relation. But if I somehow add another ordered pair, let's say that involves 4. If I just add one ordered pair that involves 4, 2, 4, then let's see if I'm saying 2, 4. Okay, if 2 is related to 4, then that's it. This is your Halsey diagram when 2 is related to 4. The moment 2 becomes related to 4, now you can see that from 1 you have an upward path, so 1, 4 automatically has to be here for this relation to remain as foci. Okay. So anyways, because of this property that there is an order in the elements, because of this property only, these are the things that comes into, that you observe that these things will happen. You will find some element which is a minimal element. You will find some element which is maximal elements here, 3 and 4 both are maximal elements, right? You know what a minimal and maximal element is. Now in this video, before moving on to lattice, what I wanted to give a definition and short summary, but maybe video may get long. Okay, so as I said that because in a partial order relation, there is an order among the elements that are involved in ordered pairs, and because of this, these are the things that may be there or may not be there. Means maybe in your element, like the example just I showed, there were two maximal elements, 3 and 4. So there was not any greatest element. As you know that for a greatest a unique maximal element is a greatest element. If you don't have a unique maximal element in your partial order relation, then there is no greatest element in your equation. And that's what we are going to see right now. What is the minimum cardinality of any partial order relation? What is the smallest partial order relation possible? So clearly it is not an empty set, means empty relation. It cannot be, because it has to be reflexive. But then again, as you know that apart from reflexive pairs, if you don't add anything, it is a partial order relation. For reflexive pairs, isolated vertices, because between two distinct elements there is no relationship. So for this relation, we know what is the partial order relation for this. Partial order is 1 1, 2 2, 3 3, 4 4. Now for this relation, all of your elements are both minimal and maximal. Minimal because there is no any node from which an upward path leads to any of these nodes. So all of them are minimal nodes. And why they are maximal? Because there is no upper path from this node to any other node. What I mean to say is that there is no element that is related to this element, and there is no element to which these elements are related to, and that's why they are maximal and minimal. So far, up till now, this is your maximal elements, and these are your minimal elements also, up till now. Now can I say that there is any greatest element? As you can see, is there any element with to which every other element is related to? No, so there is no greatest element. And similarly, is there any element that is related to every other element? No, so there is no lowest element so far. So greatest element and lowest element do not exist till now. For this partial order relation, there is no greatest element, there is no lowest element. Now let's say if I start adding the ordered pairs that have different elements, let's say 1 and 2, 1 and 2. So of course, from 1 you have 2. Now the moment you add, do you need to add any other ordered pair to conform antisymmetric or transitive? So far not. But the moment you add this, what happens is that 1 is no longer your maximal element, because there is an upward path to 2. So there is an upward path to any other element, or 1 is related to any other element. So 1 is no longer a maximal element. And 2 is no longer a minimal element, because there is some other element that is related to 2. So 2 is no longer a minimal element. Now let's say if I add any other ordered pair, let's see if I add 3 and 4. Let's say if I add 3 and 4. Now there is, if I add 3 and 4, then 4 is no longer minimal element, and 3 is no longer maximal element. Okay, but as you can see, you still have 2 minimal elements and you have 2 maximal elements, right? Now 1 and 2 are comparable, 3 and 4 are comparable. 1 and 3, 1 and 4, 3 and 2, 3 and 1. They are not comparable. So the elements that are in different connected component in your Hasse diagram, if there are two different components, so elements in the different connected component, definitely they are incomparable. Now, if I add an ordered pair, let's say 2 and 4, just adding 2 and 4, can I leave it here? I can't leave it here. Adding 2 and 4 means I have to add 1 and 4 also, because I have to take care of transitivity. I want this to remain partial order. So if I add 2 and 4, then my Hasse diagram will be like this. But the moment you add 2 and 4, now as you can see, 2 is not any longer your maximal element, and 4 is still my minimal, sorry, 4 is still my maximal element, 3 is still my minimal element, 1 is still my minimal element. Now as you can see that now you have a unique maximal element. The moment you have a unique maximal element, now there is an upward path from every node to this node. So the moment you have a unique maximal element, that is your greatest element also. So now your greatest element exists. So when your greatest element exists, when you have a unique maximal element. Now I'm asking you this question, that if someone says, okay, if the question is that there is a unique maximal element, what do you conclude? You conclude that that is the greatest element. What I mean to say is that it will always happen that a unique maximal element is the greatest element. Okay, forget this partial order set. I am just saying that 4 is your unique maximal element. Then try to have, try to make a Hasse diagram such that 4 is not your greatest element, and you won't be able to do that. If you have any element that does not have an upward path to 4, that's what you have to show. Okay, so let me say, let me take 1 and say that from 1 I won't have an upward path to 4. Okay, so let's say 2 is here, 3 is here, 3 is here. It cannot be like this because all of them are maximal elements and 4 is no longer a unique minimal. So I don't want this. So let me connect 2 with 3. Let me connect 2 with 3. Now 2 is not a maximal element, but 3 is a maximal element. I don't want 3. I don't want that. So let me connect 3 and 1. Let's say I am connecting 3 and 1. Now 1 is a maximal element. So I have to connect 1 to 4. So you cannot have, means you cannot make a Hasse diagram in a way that you have a unique maximal element but that is not greatest. It cannot happen. Okay, what I am trying to say is this, that if the relation is partial order, then there must exist maximal and minimal elements. Okay, now if that maximal element is unique, then it is greatest element. If that minimal element is unique, then it is lowest element. Okay, so maximal and minimal elements has to be there in your partial order relation, as we have seen that if you have the smallest, if you have the smallest partial order relation, then all the elements are maximal and minimal, and as you add more and more ordered pairs, the number of minimal and number of maximal elements may decrease, and ultimately if you add enough ordered pairs such that maximal elements, number of maximal element becomes only, is unique, is only one maximal element, it means what? It means it's the greatest element. So what I mean to say is, if you have a unique maximal element, then that is the greatest element, or your Hasse diagram is bounded from upside, because 1 is your greatest, 4 is your greatest element. Now 4 is your greatest element, means that your order is bounded from up. What I am, why I am saying bounded, this is your finite set, but your partial order relation may be defined on an infinite set, like like a relation defined on integers or relation defined on set of real numbers. Now, in that infinite set, if you have a greatest limit, then you cannot go, means your Hasse diagram cannot go, unlimited way upward. Okay. Similarly, if you have a minimal element that is unique, so here 1 and 3 are minimal elements. Let me add an edge from between the two. Means if I add 1 to 3, then it's fine. I just have to do this. Okay. So let me add 1 to 3. And because of 1 to 3, 1 to 4 also come. So the moment you add this, now 3 is no longer your minimal element. As you can see now, 1 is your minimal, unique minimal, and this is lowest element also. So if you have a unique minimal element, then that unique minimal element is your lowest element. If you have a unique minimal element, then that unique minimal element is your lowest element. And so we say that your Hasse diagram is lower bounded, which is bounded at the base. Okay, you cannot go, you won't go infinitely deep. So about the rest of the stuffs like upper bound, lower bound, least upper bound, and greatest lower bound, you already know that. But I will make another video on that also. Means I wanted to cover it in this video only, but I am tired. Thank you very much.